Hello, welcome. Monday, kitchen table chemistry, May 18th, and today we want to be able to describe metallic bonding. So the only issue we'll really discuss today is bonding between metals, which is metallic bonding. So we're only talking metals here. So here's the story. What is metallic bonding? I put it all in one slide, probably too much, but in metallic bonding, the outermost valence electrons of each of the metal atoms overlap with a large number of neighboring atoms. As a result of this overlap, the valence electrons continually move from one atom to another and are not associated with a specific pair of atoms. So what we have here is the ability of the electrons to move. The electrons are mobile. So in short, the valence electrons in metals, unlike everything else we're ever going to see, are delocalized and capable of wandering freely. I love that term. And that throughout the entire sample. This is why metallic substances conduct, because the electrons are equally attracted to every one of the metallic atoms. And after the metal has lost electrons, it becomes a metallic ion. So the atoms in an electron, the atoms the electrons leave behind become positive ions, and the interaction between such ions and valence electrons gives rise to the cohesive or binding force that holds metallic crystals together. So it is this sea of electrons, as it's sometimes called. Now I'm going to go to another slide. In metallic bonding, it's often described as an array of positive ions in a sea of electrons. You will never lose points for using this term, sea of electrons. It's how many people will describe metallic bonding because the electrons are mobile. They are delocalized, meaning that they don't belong to a specific metallic atom. They are delocalized. They are mobile or able to move. And we're only talking the valence electrons here, only the outer electrons. And this is why they conduct electricity, because you need to have a flow of electrons through the substance in order for it to conduct electricity. So that flow is accomplished really only in metallic things like this and allows them to conduct. Okay. Here is a little bit of a diagram. So each of these positive ions is a metal ion, and around it are all these electrons. Notice that there is no order to the electrons. And these electrons are mobile. They're able to move. And because they are all negative and the metallic ions are all positive, we have a very, very strong, tight attraction between. So it's different from ionic, which is very, very much a static attraction. Here we have electrons that are mobile and can be moved. This also allows us to combine different metals together. With ionic crystals, we had distinct formulas based on the number of valence electrons that were transferred. So AlCl3, MgO. With metallics, it can be much, much more variable. Because of that, we tend to see what are called alloys, and these are metallic mixtures. And these will have variable formulas because there is no set number of valence electrons that are moving, so it allows us to have a variable formula. Sterling silver, if you've got any of that around, it might have jewelry and that, or something that you serve food with. 92% silver and 8% copper, you can put them together, you get the effect of having a very nice silver. It's a little bit more durable. And cast iron, which is what I like to cook with, 96% iron and then 4% carbon, again, setting up carbon, not a metal, but sets up in a very much a metallic manner here. Stainless steel, 80% iron, 18% chromium, 1% carbon, and 1% nickel. If you don't like stainless steel, if it bothers you, it's probably because of the nickel. And I thought I had another one there. Do I have another one? Oh, spring steel, and that because you need it to be stronger and to remember a shape, has chromium in it. And then surgical steel, and that 67% iron, 18% chromium. By the way, surgical steel, in my experience, does not ring out the metal detector at the airport. I have a knee that is full of it, and it does nothing in that at all. It has a little bit of molybdenum in it as well. Okay, there's many other things going on here, but I think for a COVID lesson, this is more than enough. I have a few questions for you about metallic bonding to answer so that you can hopefully explain this. And otherwise, this will be it for metallic bonding. Tomorrow, we will start covalent structures. I hope everything is going well. I put in an agenda or an itinerary for you for the week, most of which will be spent on covalent bonding. If there's any residual questions on ionic stuff, I can definitely go over it. All right. Hope you're well. Hope you're safe and enjoying the nice weather. Take care. Bye bye.